I'm going to be talking about the tools we've designed to create generic adversarial attacks. I'm sure everybody at this point is familiar with what they are. We want to make errors in machine learning models. But there's a bit of a problem with this from kind of a practical perspective, as we've heard in some of the previous talks, which is that a lot of the stuff, we have a lot of attacks, but a lot of them are on images or something that's like an image. And images are really nice to attack because they're just numbers. And machine learning models ingest numbers, so converting them is very easy, and making changes to them is very easy. But when we go from something that's like an image to something that's like text or files, there's a bunch of problems that we now have to solve that kind of break the previous attacks. For those of you familiar with problem-space attacks, this is kind of what we're talking about here. The first issue is first we have to convert it into something the classifier can understand. And what that means is we're going to have to create some sort of feature representation. But that feature representation, it may be hard to invert it, right? If I give you the features, you might not be able to reverse engineer the file. And even after we get the features, we then have to somehow transform the input. With images, it's really easy. We just have to add and subtract numbers. But with something like a file, what does that mean? How do we go from, I want to increase feature 4 by 0.2 to that's how I want to transform the file? And there's also a question of validity, right? There's an idea that, with images, all you have to worry about is that your inputs are bounded from 0 to 1. But for text, maybe you want to make sure you don't delete the string, because what's the point of an adversarial example at that point? For files, if you have malware, you want to make sure that even those being classified as benign, it's not because you just removed the malicious functionality. So when we go from taking a normal adversarial attack to what is a generic adversarial attack, all these problems kind of prevent us from implementing these on other fields. And machine learning spans a whole bunch of topics. So without tools to evaluate adversarial attacks, it's kind of hard to warn people and say, look, there's a big threat out here. And then they say, well, how do I evaluate this threat? And if I can evaluate it, how do I even protect myself against it? When we look at some of the prior work, there's a lot of stuff out there that looks at non-image adversarial attacks. But some of the problems we run into is, the research papers. You kind of publish the code, you say, here's the experiments, and then, a few years later, you don't really care, right? Your libraries are out of date. There's new and better attacks that are coming out there. A lot of them are limited in scope. We see there's a lot of stuff looking at malware and how you create adversarial examples for malware detectors. But there's not really examples of, well, OK, I have malware, but how do I translate that to some other domain? Theoretically, it could be possible, but it's a lot of a lift to be able to do that. We saw something about how, for machine learning practitioners, they may not be familiar with AML. And when they then get this tool, they may not know how to use it. There's not really a UI for them to access. They may have to look through the code. There's a lack of documentation. And in some cases, there's this concern that if we release tools out there, that people are going to misuse these tools. They're going to create adversarial examples to attack real systems. But at the same time, we're kind of preventing people from having access to tools to evaluate their systems and prevent that. So these are kind of the problems, and that's what we're trying to solve with this URET tool, right? We've created this end-to-end adversarial attack for theoretically any input type. We have this configuration file interface so that when you want to do an attack from a basic level, all you have to do is just specify the parameters within the file, and then you can run it. And you can give that file to somebody else, and then they can run it and do the same evaluation. And for the more advanced users who maybe have some input type that we haven't initially supported, or they have some new task that has this weird loss function, you can make those changes through a kind of a standardized interface so that it can be easily ingested into the tools. So like some prior work, what we've done is we've said, look, an adversarial attack at a generic sense is really just a graph exploration problem. We have this huge graph that we don't really know where the adversarial examples are, and we just need to follow edges, which are input transformations, in order to discover our adversarial example. Now I'm just going to go into the 5 kind of major components. You can find more details in the paper. But the first one is how do we go from node to node? Right? How would you do the ranking? And we provide a variety of different algorithms in the implementation. And the reason for this is because people may have different needs. Maybe they need to get the highest success rate. Maybe they're trying to do adversarial training and they're time constrained. So they don't necessarily need every sample to be adversarial, but they need to be at fast because they can't add that kind of training overhead. We have the input transformers. So this is how we define the edges in the graph. Input transformers, the interface is really you define a set of actions that you can do. So for like text, you can add, subtract, substitute characters, and you define the constraints. This is kind of the first level of validation where you say, look, I want to make sure that I'm only using alphanumeric characters. Or I want to make sure that if I'm going to increase the length of a string, that that string can only increase by 50%, and then afterwards you have to figure out some other transformation. We then have vertex scoring. So this is your typical loss function that you're optimizing to create your adversarial example. We have classification loss, which is the traditional one, but we also have this distance-based loss, where maybe you say, you know what, I really want to use PGD and attack the feature space. And so we say, OK, well, you have some adversarial target. We can do a distance-based loss, and you can try to optimize towards that to reverse engineer a valid input with respect to those features. And again, if people have some wacky thing that they want to come up with, they can define that, and URET can ingest that and use that to measure the fitness of the input states. Graph searching. This is very simple. Really, it's mainly beam search. But maybe you're kind of like, I don't really want to worry about exploration exploitation. So that's why we have this simulated annealing, which is a temperature-guided search that at the start of exploration will say, look, I'm just going to keep nodes that are likely to maybe reward me in the future. But as I get closer to the end of exploration, and this is kind of, there's a time limit for simulated annealing, that I want to just start keeping the best node every time. And the final thing is input dependency. So this is a problem that you see with adversarial attacks that try to write a wrapper over image-based attacks, which is they can't really enforce feature dependencies, right? Maybe you have a tabular data set, and you have a spending, savings, and total amount. And if you change either one of the first two features, you should probably change the third feature as well, because otherwise nothing makes sense anymore. So yeah, those are the 5 components. I'm just going to quickly go into the experiment results. So within the paper, we did 2 more experiments, one on malware binaries, so directly on the file themselves, not the feature vector. And we also show some adversarial training results as well using this tool. But for the purposes of this talk, I'm just going to look at the HMDA data set, which is a tabular data set that is predicting loan approval, and the DGA data set. So the task here is that given a domain name, is it a real domain name, or is it one that's produced by a malware trying to evade detection and trying to establish communication to an external server? One thing to note is that all of these classifiers, we didn't train any of them. We were given to them by a third party for evaluation. And when we did the evaluation, I don't know if this is traditionally done, but we made sure that all the samples were correctly classified, because you don't want to get this thing where you say, oh, I fooled it, but it turns out it was wrong in the first place. So there's a lot of numbers here. You don't need to really worry about the specifics of these numbers. This is just something to look at. The main thing to focus on is that the tool does pretty good. We have a variety of algorithms. They all have a variety of success rates. What's interesting, as we said, is that maybe you're worried about time, because brute force, you probably expect to do the best. It's exploring the entire graph at every node. But if time's kind of your concern, you could say, OK, well, I'm going to use a different algorithm. The lookup table algorithm, for example, does kind of brute force on a small level to build a history, and then uses that history to do the exploration in real time, but it kind of ignores the input state at that point. It just relies on the history. And as we can see, it really cuts down the time, but it also kind of sacrifices performance, since it's no longer considering the input state. Maybe consistency is what you want. You know that you have a certain amount of time that you're willing to spend for the exploration, and brute force, especially for some of the larger search spaces, is too expensive for you. So you look, I want to make sure that it's always 1 second, and that's what simulated annealing offers you. It kind of just does random explorations, but you know that within that 1 second that you're always going to end at that point. And we can switch between domains. So previously, we were attacking a tabular data set. We were looking at 7 of the features and attacking them. And now we're going to switch to a text data set. And the only thing that's changed, really, is the configuration file saying, look, I want you to use text transformers instead of the categorical transformers. So we see, again, the results. There are some issues sometimes when we change the task to maybe try to reverse engineer features. We see that there's a decrease in the success rate. which, is to be expected. What we're trying to do here is we're not trying to transform the input directly, but we're trying to get to some target, and maybe the target's just not possible, right? And that's a problem with, the problem space attacks where you attack in the feature space, is you create a feature vector that just isn't possible to realize, and the graph does its best. You also see that there's an increase in the amount of time, especially for brute force, where it's spending way more time because there's a lot more things it has to consider when it does an exploration on the node, and it may not be taking optimal paths anymore. If you look at the model guided, so this is, in our case, was a reinforcement learning approach, that it cuts down the time way faster than the brute force. So those are kind of the quick results. There's some additional results if you're interested on doing it on malware, as I said, doing adversarial training. So we saw one of the other talks within our paper as well that adversarial training with PGD in the feature space isn't very effective defense against realizable adversarial examples. But if you can actually create the adversarial examples through a tool like this, for example, that you can start to defend. And it's important that we have these tools to kind of do an evaluation. We can warn people about the dangers of adversarial examples, but unless they have the tools to do that evaluation, they won't care. They'll say, okay, that's just a research problem. We also need to realize that not everybody's a security researcher. That a lot of them, are maybe engineers just trying to implement the models, and so they don't get what it means to create an adversarial example, to evaluate it, and then to create defenses and analyze that. So you want to maybe keep it simple for them. You want to keep it flexible, because even if you give them saying something, look, you can take my malware attack and you can turn it into a tabular attack, that's maybe something they just don't have time to do. So we've released the tools publicly. There may be a question again of, oh, what about if somebody uses it? And yeah, hopefully we hope people use it. Some people might use it for bad, but at least we're going to have people who have access to penetration testing tools. In other domains, we have penetration testing tools, so why not for machine learning? Yeah, and that's it. I'll take questions.